this equation, to the thermal resistance concept. Okay, thermal resistance concept. Okay, so what is the thermal resistance? Is a thermal resistance is the method to analyze heat transfer by identifying the heat transfer mode as a resistance. Okay, never mind, we will look this throughout throughout the slide. Okay, first we know that for heat conduction, okay, this is the equation, the basic equation for the heat conduction. Okay, from Fourier's law, heat conduction can be calculated if you know the thermal conductivity, okay, the area, the temperature difference, and the thickness of the system. Okay, this is from the chapter 1. Okay, so you know that heat conduction can be calculated by Fourier's law. Okay, where you can calculate when you know the thermal conductivity of the solid object, the area that normal to the heat transfer, the temperature the temperature difference between one side to another side, okay, and the thickness or the length of the system. Okay, so if you look to this equation, we can introduce a resistance concept by combining the terms that related to the conduction. Okay, so this KA over L, okay, so this term KA over L times delta T, okay, so it's basically 1 over R resistance due to the conduction. Okay, so we can see that R conduction can be simplified into the L over KA. Okay, because this resistance is the parameter that influence the conduction transport. Okay, so this conduction resistance is due to the thickness, due to the thermal conductivity, and due to the area of that particular system. Okay, so by replacing this L over KA with the R, okay, so you can get the Q conduction basically can simplify into delta T over R conduction or R wall. In this okay, in the slide I put R wall. Okay, it's also can write as R conduction, because the R wall is basically R conduction. Okay, so that the concept of the thermal resistance can be derived from the original calculation of the heat conduction equation. Okay. If you have any question, you can ask me or you can write in the chat. Okay. So the basically the thermal resistance concept is likely similar to the electrical resistance concept. Okay. So I think you have learned the electrical technology in your first year. Okay, so you may still remember the electrical resistance. Okay, so this concept is same like the thermal resistance. Okay, so in electrical resistance you can calculate the resistance because of a difference in the voltage, okay, and due to the current flow. Okay, but in the thermal resistance the current flow now is changed to the heat flow, and the voltage difference is changed to the temperature difference. Okay, so if you can calculate the current, okay, by knowing the voltage difference divided by the total resistance, so you also can calculate the heat transfer, okay, which is known as a heat flow, heat rate, okay, if you know the temperature difference divided by the total resistance. Okay, so if you remember in your calculation electrical analogy or electrical system, the current flow will be always constant, okay, regardless of any process, it will be constant throughout the um, line of the electrical. Same goes to the here, heat flow will be constant throughout the um, system that pass through, whether it is a heat conduction or heat convection. Okay, the difference is due to the voltage for the case of the electrical, but in the heat transfer the difference is the difference is due to the temperature. Okay, okay, so using this thermal resistance concept, okay, so you also can derive another resistance due to the convection, okay, as well as the radiation. Okay, so look here, basically you can calculate the Q conduction, okay, if you know the temperature difference divided by R conduction. Okay, same goes here, Q convection you can calculate if you know the temperature difference divided by R convection. Okay, same goes here, if you want to calculate Q by the radiation, you can calculate by delta T divided by R to the R radiation. Okay, so other than you are using the basic equation of conduction, convection or radiation, you also can calculate the conduction, convection, radiation if you know the resistance, the thermal resistance due to the conduction, convection or radiation. So the unit of the resistance, okay, is a Kelvin per unit watt. Okay, is basically how many temperature increase, okay, per unit heat rate. Okay, okay, so using this concept of the thermal resistance, okay, we apply back to this system that we consider in the early slide. Okay, so you know that here you have the convection, okay, so you have, this is the convection, okay, this is conduction, and this is another convection. So if we want to indicate the thermal resistance, okay, okay, using the concept of resistance, we call it, this is a thermal resistance diagram. Okay, so you have convection at the right side, sorry, at the left side, where there is a hot fluid, okay, and then you have conduction in the middle side, where you have this wall, okay, and you have the convection on the right side, where you have a cold fluid. Okay, so the temperature of each surface or each section representing the temperature before the resistance. So this is a T surrounding at hot region. This is a T surface, okay, here T surface, sorry, this one T surface at hot region that face to the left side of the wall, okay, and this is the temperature of the right surface that face to the cold area, TS2, and this one is a fluid temperature for the cold region or cold area. Okay, so basically the thermal resistance can be indicated by this diagram, okay, where you have the temperature difference, okay, due to the difference in resistance. So basically you have one resistance due to the convection, second resistance due to the conduction, third resistance due to the convection in the cold side. So having these three resistance, you can combine this resistance to calculate the total resistance. Okay, so which is R total of these three resistance. Okay, so if you look here, okay, you can find the total resistance by combining all the resistance, okay, of the wall starting from the hot temperature region to the cold temperature region. Okay, so R total is basically, okay, if I need to write at the beginning, R total is R due to the convection, okay, in the hot side, R convection hot plus R conduction the wall plus R convection in the cold side. Okay, so what is the R convection for the hot? This one. Okay, what is the R conduction for the wall? This one. Okay, and R convection for the cold is this one. Okay, so if you want to calculate total resistance, okay, you can calculate the heat transfer through the cold temperature from the hot. Let's say this is a T hot minus T cold. Okay, so from the highest to the lowest. Okay, however, you also can calculate the temperature in between TS1 and TS2 if you know the resistance in each section. Okay, for example, if you want to calculate TS1, okay, you need to know the resistance only for the hot side, okay, due to the convection, because if you look at this region, okay, you can calculate Q equals to delta T over R. So this is the original equation for thermal resistance in any heat transfer mode. Okay, so for this region, the temperature is changing from T surrounding 1 to TS1. So T surrounding 1 minus TS1 equals to R resistance due to the here only due to the convection in hot area. Okay, so what is the R convection for the hot? Only this. Okay, so this Q basically is the same as this Q. Okay, like the analogy of the current. in the electrical calculation. So electric current will be same regardless of any component that you want to use, but the difference is the voltage difference. Okay, in this case the difference is due to the temperature value. Okay, so how this can assist you in the conduction analysis? Okay, so this is an example of composite wall. Okay, what is the composite wall? Is basically a layer of different system that have different thermal properties. Okay, so like this you have the hot area, you have the cool area on the left and right, and in the wall you have three different layers, okay, with three different thermal conductivity, Ka, Kb and Kc. So by using the thermal resistance concept, you can simplify the calculation with calculation of total resistance from left to the right. Okay, because the temperature movement from left to the right. Okay, by introducing the resistance throughout the system, throughout the wall. Okay, first you have the convection on the left side. You have next one, you have the conduction in the first layer, conduction in the second layer, conduction in the third layer, and finally convection in the hot area, the cool area. Okay, so the R total basically combination of this one. Okay, R1 R cool, R hot plus R1 RA plus RB plus RC plus R convection in the cool area. Okay, so this is the total resistance. Okay, so if you can calculate the heat transfer rate for this system, so you can calculate by calculating the R total. Okay, in the textbook they introduce you U term. What is a U term? U term is another words to represent the total resistance of the multiple layer. Okay, so overall heat transfer coefficient is basically R total terms, okay, in heat transfer coefficient, okay. Basically whether you want to use R total or you want to use U is the same thing, okay, because this one, by assuming that the area across the system is same, okay, but in my case I prefer to use R total rather than U. Okay, so if you find U terms in the textbook, so don't confuse. So U is basically the combination of R total with the same area of cross section. Okay, so basically this one, okay, is actually same as delta T divided by R total. Okay, it's the same thing. Okay, so R total is basically 1 over UA. So you can just change this into the R total equation. Okay, we look to this example. So how the thermal resistance can use to analyze the heat conduction equation under one-dimensional analysis. Okay, this is example 3.3. If I can go to the textbook. Okay, Okay, in fact, you can go to the description in the textbook. It's much more details, okay, compared to my slide. Yeah, this one. Heat loss through a double pane window. Have you heard about double pane windows? Okay, double panes window, sometimes we call it a double glazing window. Okay, we have two layer of glass. Okay, we have two layer of glass, okay, at which in the middle of, in between the glass, you have a third layer, or you have a additional layer that can control the heat transfer. Okay, normally we put air, because the air is the cheapest material. Okay, the cheapest material, and can have greater impact, okay, significant impact in reducing the heat transfer. Okay, so consider a 0.8 meter high. Okay, the height of the window is 0.8 meter high and 1.5 meter wide. Can you see my slide? Okay, okay, so this is the figure of double pane window. Okay, each glass have a thickness of 4 millimeter thick, okay, with K value 0.78, okay, separated by 10 millimeter wide stagnant A space or A gap, okay, with K value 0.026. Determine the steady rate of heat transfer through this double pane window and the temperature of the inner surface for a day during which the room is maintained at 20 degrees Celsius and the outdoor temperature is negative 10 degrees Celsius. So this is not our environment. It's a cold environment where the outside has a temperature of so this is outside and this is the inside. The other way around. So basically this is the inside. Okay, this is the outside. Okay, meaning the outside temperature is lower than the inside temperature. So of course, whether inside or outside have higher temperature, the heat transfer will move from high to low. Okay, that is the principle of the heat transfer movement. So heat will move from the high temperature to the low temperature. Okay. So okay, you draw this diagram. Two glass with in the middle of a gap. So you have you have a glass here on the first side, and you have a glass in the other side, and you have the inside area where the heat transfer, where is the temperature is 20. So the T surrounding inside is a 20 degrees Celsius, and the heat transfer coefficient of the inside is a 10 watt per meter squared Kelvin. Okay, this one. Okay, while the outside is a negative 10, and the H outside is the 40 watt per meter squared Kelvin. Okay, so this is diagram that you should draw. Okay, remember when I try to make it as a routine or as a standard way of solving the problem. So start with sketching the system by putting the important dimension, okay, and important parameter that given from the problems. Okay, so once you complete the diagram, then you start with some assumption. Okay, but in this case there is no assumption, right? There is no assumption. I suppose there is should be assumption here. Okay, never mind. Um, okay. After this diagram, you should put some assumption to assist your calculation. So what is the assumption that relevant to this problem? Okay, actually you can take from the problem statement here. Okay, so of course this is one dimensional analysis. So this is one dimensional analysis of heat transfer. Okay, and then what else? Number two, if you look here, the thermal conductivity is given and constant. Okay, so we can see here the constant value of thermal conductivity. Okay, okay. You can mention also for glass and air. Okay, because this is the only K value is given in the textbook, in the problem. Okay, what happens if the thermal conductivity is not given? Then you need to go to the table properties and then find this the material, the glass and the air. Okay, so you know how to find it. So go to the table if you can. Where is it? Okay, for the glass, for example, where is the glass? Is it given here? This is gas, solid. I think building material. This one, glass, gypsum, cellular glass. This one. Okay. 0.05. Okay. So there is one glass here, cellular glass, but this is board and slab. Looking for specific glass. Okay, and air. Where is the air? Air you can go for the gas. I think air is in the first part. There is the air. Gas. This is gas constant. Boiling and freezing point. What is the air? Common food is miscellaneous material. Oh, there is I think another glass here. Yeah, this one. Okay, properties of miscellaneous material. Okay, table A8, this is a glass here. Okay, 0.7 for window. So clearly this is meant for the window. For the air, I think there is a specific table for air. You need to find table of air. Where is it? This one, yeah. Properties of air at 1 atm. So you can find at I think this is 20 degrees Celsius. So this is the K value. Okay. So you can assume that the K value is taking from temperature 20 degrees Celsius. Okay, because you might not sure what is the temperature of the exact temperature of the air. Okay, that is if the K value is not given. Okay, so you need to take from the tables. Okay, next one. Once you know the K value, okay, what else? The assumption. I think there is some terms here that you can find from the problems. This one, the steady rate. Okay, meanings this problem. Okay, analysis under steady state condition. Okay, and this is under steady state condition, because if unsteady, that means the temperature might be changed and not constant. Okay. Okay, that is I think the three relevant assumption that required in your analysis. Okay, next, after the assumption, you start the analysis. So this is your diagram. Okay, if I can so this is your diagram, schematic diagram. Okay, this is your assumption. Okay, so next one with your analysis. Okay, this is 1, this is 2, this is 3. Okay, so how to start the analysis? First you need to identify the thermal resistance diagram. Okay, I call this as a thermal resistance diagram. Thermal resistance diagram. This one. Okay, so this thermal resistance diagram is very useful in order for you to understand how many resistance is actually involved in your analysis. Okay, so because of there is 3 layers, and then you have convection in both sides, left and right. So in total you have 5 resistance, 5 thermal resistance. 1, 2, 3, 4, 5. Okay. Okay, you can see here, first they calculate the resistance in the convection left side. Okay, and then you calculate the resistance for the glass, because of the glass is identical left and right, so they calculate once only, and this equal to R1 and R3, and then R2 for the air. Okay, and R outside for the convection in the cold area, or in the outside area. Okay, so from here they combine the total resistance. Okay, combine the total resistance. Okay, don't forget to add 2 glass, because you have a 2 glass here, and you can calculate the total the steady rate of heat transfer through the window from the beginning of the temperature 20 on the hot side to the temperature at the cold side. Okay, 20 minus 10, which is the 30 degrees Celsius, divided by R total. So you got this value 69.2 watt. Okay, so this is heat transfer throughout the system regardless of any layer. Okay, so if you want to use or if you want to find the temperature in any section of this system, you can use this value 69.2 but with the corresponding resistance in the particular temperature section. Okay, so this means the inner surface temperature can be calculated if you know the Q and the resistance corresponding within this temperature difference. Okay, because originally this one is actually Q dot equals to delta T divided by R. Okay, so if you want to find between T1 minus T1, okay, T1, where is the T1? T1 is here. Okay, so this is a T1. Okay, yeah, this one is T1, this one is a T2. Okay, this one is T3, this one is T4, this one. Okay, so what is the corresponding resistance within this range is R due to the convection in the inside section. Okay, this one. Okay, okay, any question? So this is an example of how we can use a thermal resistance concept whenever we have dealing more than a single layer. Okay, because if you look previously for single layer we can use a simple calculation of heat conduction, but if you have a multiple layer, then the use of thermal resistant approach is more useful and easy and simple in order to combine the resistance concept. I think by understanding this example, okay, you can further you can do more example related to the thermal resistance analysis for the plane wall. Okay, so this is only for the plane wall. In fact, next we will go to the how to use the thermal resistance analysis or thermal resistance concept in case of cylinder and in case of the spherical. I think yeah, this one, heat conduction in cylinder and sphere. We will do it in the later parts. Okay. Any question so far? Okay. So if you look the example just now is basically a simple a multiple layer which arranged by the series of the layer. Okay, what happened if this arranged in the vertical position? Okay, originally it is arranged as in a series. Okay, what happened if this arranged in a parallel resistance, parallel arrangement? Okay, we will look this in the next class. Okay, of course tomorrow to discuss the difference between the parallel thermal resistance and the series thermal resistance. So here is basically is a series. Okay, it's a series thermal resistance. You are facing the same layer at the different at the same layer at the same direction of a heat transfer. Okay, any question? So if not, I think that's all for today. You can try to understand the example. Okay, and I will see you again in the tomorrow class. Okay guys, with that I end my presentation. Thank you very much for your attention. See you again tomorrow. Okay, Assalamualaikum warahmatullahi wabarakatuh, and good day. Thanks a lot.